Alright, this is Chapter 1, Section 2, Integrals as General and Particular Solutions. So, what is a general solution? Well, you get this differential equation where y is the independent variable and x is the independent variable, y is the dependent variable, x is the independent variable, and you get this function f of x. Now, for this case, we want this function to just be dependent on the independent variable and have no dependent variables in it. If we can do that, then I can find my y of x by just integrating. Okay, so to get a particular solution, what I have to do is add one extra thing to this. I add what I call an initial condition. I give it an initial x value and an initial y value, and that conforms my solution through that point. So here's an example. Here is our differential equation, and you notice that it only has 2x plus 1, only independent variables on the right hand side, so I can use this integral. I'll separate it into two, and then I'll do the integral, and I get my x squared plus x plus c function. And since I don't know what c is, this gives me a family of solutions. So how do I see this family of solutions? We want to graph it using Maple. To graph it using Maple, we're going to use this plot command. Well, this plot command, so you just type in plot, curly bracket, and then since I want to plot 7 different functions, I'm going to have Maple create those 7 different functions for me. So inside the curly brackets, I have 3 things. I have my function I want to plot, I have this $, and then I have the range of c values. So the $, is a sequence command. It tells Maple to look at the range of c values and substitute them one at a time into the c of our function, and it creates these graphs that you see below. Well, how does the c equal minus 3 dot dot 3 work? Well, it starts at minus 3. You see down here the bottom y graph, and then increments by integer values of 1 all the way through until it gets to 3. So it makes 7 plots. What is the x equals minus 5 dot dot 5? That allows Maple to know that I only want x to range between minus 5 and 5. And the y equals minus 4 dot dot 4, that tells Maple that my y range only goes between minus 4 and 4. And you get to choose all the ranges of x and y so that you can see the best picture of your graph. Alright, we've already done this integral. Alright, we've already done this integral, except I'm going to add this initial condition right here. And I add that initial condition of at x equals 0, y needs to equal 3. So I got to figure out what my c value is for that. So I'm basically plugging in my x value to my solution and forcing it to equal 3. And you look at this, that c has to equal, and I can graph that solution. We're going to be making some more plots with Maple. So again, here's the plot command. I still think I typed this in wrong. It should be lowercase p for plot. Capital P might mean something different, but you can just plug in your function and then plot it from minus 10 to 10. And then it plotted those values for me. And there's your graph. Alright, so let's look at the solution for a second order differential equation. So there's our second order differential equation. And what we can do is I know the first derivative of y of x has to be equal to the integral of g of x dx plus c. And I can solve that. Now that I know that, I can do another integral on this, and I can get this solution. Okay, another way to look at this is I'm going to use a substitution variable of v of x. So I'm going to claim the first derivative of v of x dx is equal to g, and in doing that I can claim that the first derivative of y d of x is equal to v. Now if I make those substitutions, if I take this for v and I put it back in here, I get my initial differential equation. So now I have two first order differential equations which I can solve by using my integral. So I can get v of x, and then I can solve for y of x, but I need what v of x is. I've got it up here, and I can plug it back into here, and I get the same solution that I had using the previous problem. So they both give you the same answer. It's just two different ways of looking at the same thing. Alright, so the last thing we need to do is to deal with velocity and acceleration. So we have, by definition, the derivative of the position with respect to time is equal to the velocity. The derivative of the velocity with respect to time is equal to the acceleration. And then if I plug what v is into the acceleration derivative, you'll get that the second derivative of x with respect to the second derivative of time is equal to the acceleration. That's all you need to know to do velocity and acceleration problems. Okay, so let's do some examples. So I have my differential equation right here, and I have an initial condition. So let's solve for that. So I have no dependent variables on the right hand side, so I can solve it through an integral. And so if you do this integral, you get this answer. And now I need to find out what c is. So x is 4, but I want y equal to 0. C has to be equal to what? It has to be equal to a minus 16 divided by 3. And then so our solution, particular solution, would be equal to this. Y of x is equal to 2/3 x to the 2/3 power minus 16 divided by 3.